Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The landscape of mathematics in the early 20th century presented formidable barriers for women seeking to contribute to its abstract and rigorous realms. Prevailing societal norms, coupled with institutional biases, often relegated women to the periphery of mathematical research, limiting their access to advanced education, mentorship, and professional opportunities. Elisabeth Lutz, a name perhaps less familiar than Emmy Noether or Sofia Kovalevskaya, navigated this challenging terrain with intellectual tenacity and ultimately carved a significant niche for herself in the field of number theory. Born in France, Lutz's early education revealed a distinct aptitude for mathematics. Her academic journey led her to the University of Strasbourg, a university with a strong mathematical tradition. Strasbourg, having shifted between French and German control during the late 19th and early 20th centuries, fostered a unique intellectual environment, blending different mathematical schools of thought. This exposure likely broadened Lutz's perspective and contributed to her later research. The faculty at Strasbourg provided a stimulating environment, encouraging her burgeoning interest in abstract algebra and number theory. It was within this environment that she began to focus her studies, drawn to the elegance and intricate structures inherent in the study of numbers. Lutz's intellectual trajectory was significantly shaped by the mathematical currents of her time. Number theory, with its long and storied history, had entered a period of profound transformation. The development of abstract algebra, particularly the theory of fields and rings, provided powerful tools for tackling classical problems. Furthermore, the emergence of $P$radic analysis, pioneered by Kurt Hensel, offered a radically new perspective on the nature of numbers themselves. These developments created fertile ground for new investigations, and Lutz found herself drawn to the intersection of these ideas. Her doctoral thesis, completed in 1937, stands as a testament to her intellectual prowess and her ability to grapple with cutting-edge mathematical concepts. Entitled Sur l'équation requesine x cubed menenter below dans les corps $P$radix, which translates to on the equation requesine x cubed menenter below in $P$radic fields. Her thesis explored the arithmetic of elliptic curves over $P$radic fields. This work, while initially met with a somewhat muted reception, laid important groundwork for subsequent research in arithmetic geometry. The relative lack of immediate acclaim can be attributed, in part, to the novelty of the field and the limited number of mathematicians then working in this specific area. However, its significance has become increasingly apparent with the passage of time. To fully appreciate the context and importance of Lutz's thesis, understanding the concept of $P$radic fields is essential. In classical number theory, mathematicians primarily concern themselves with integers, rational numbers, and algebraic numbers, roots of polynomials with rational coefficients. The $P$radic numbers, however, offer an entirely different way of completing the rational numbers. This completion is based on a different notion of distance, one that prioritizes divisibility by a prime number $P$. Specifically, the $P$radic absolute value of a number measures how divisible it is by the prime $P$. The more divisible, the smaller the number is in the $P$radic sense. This seemingly counterintuitive notion leads to a completely different world of analysis, with its own unique properties and challenges. They provide a powerful tool for studying Diophantine equations, which are polynomial equations where one seeks integer or rational solutions. The $P$radic numbers offer a complementary perspective, allowing mathematicians to analyze these equations locally, prime by prime. The study of elliptic curves, which are curves defined by equations of the form $² equals sine x cubed plus ax plus b $, where a and b are constants, constitutes a central theme in modern number theory. These curves possess a rich algebraic structure, allowing one to define an addition law on their points. This addition law turns the set of points on the curve into an abelian group, a structure that profoundly influences its arithmetic properties. A fundamental question in the study of elliptic curves concerns the nature of their rational points, which are points on the curve whose coordinates are rational numbers. Determining the set of rational points on a given elliptic curve is a notoriously difficult problem, one that has captivated mathematicians for centuries. Lutz's thesis built upon the foundational work of Lutz-Nagell and Weil. The Mordell-Weil theorem, a cornerstone of elliptic curve theory, states that the group of rational points on an elliptic curve over the rational numbers is finitely generated. This means that there exists a finite set of rational points from which all other rational points can be obtained by repeated application of the group law. While the Mordell-Weil theorem guarantees the existence of such a finite generating set, it provides no effective method for finding it. This is where Lutz's work enters the picture. Specifically, Lutz addressed the problem of finding rational points on elliptic curves over $p$adic fields. These fields, while sharing some similarities with the rational numbers, exhibit crucial differences that necessitate new techniques. The $p$adic numbers, with their non-Archimedean nature, present unique challenges for analyzing the behavior of elliptic curves. Lutz's thesis sought to understand the structure of the group of points on an elliptic curve defined over a $p$adic field. She investigated the properties of these points, particularly those of finite order, known as torsion points. These torsion points play a crucial role in understanding the overall structure of the group of rational points. While the Mordell-Weil theorem addresses curves over the rational numbers, Lutz focused on the local analog, examining curves defined over $p$adic fields. This local perspective provides valuable insights into the global behavior of elliptic curves over the rational numbers. Her work offered a new lens through which to examine these complex mathematical objects and paved the way for further exploration of their arithmetic properties. The investigation of elliptic curves over fields other than the rational numbers, such as the $p$adic numbers, necessitates the development of specialized tools. These $p$adic numbers, equipped with a non-Archimedean valuation, introduce complexities that demand novel analytical techniques when studying elliptic curves. Elisabeth Lutz's doctoral thesis directly addressed this challenge, seeking to elucidate the structure of the group formed by points on an elliptic curve defined over a $p$adic field. Her focus centered on understanding the properties of these points, particularly those possessing finite order, commonly referred to as torsion points. Torsion points are instrumental in deciphering the broader structure of the group of rational points on the curve. While the celebrated Mordell-Weil theorem provides a framework for understanding curves defined over the rational numbers, Lutz's work concentrated on the local analog, specifically examining curves defined over $p$adic fields. This localized perspective offers critical insights into the global behavior of elliptic curves defined over the rational numbers, providing a new viewpoint for analyzing these intricate mathematical objects and setting the stage for subsequent explorations of their arithmetic properties. Lutz's most significant contribution is a theorem that bears her name, often referred to as the Lutz-Nagell theorem, though Lutz-Nagell independently discovered a similar result. This theorem provides a powerful tool for determining the torsion subgroup of an elliptic curve's group of rational points. To fully appreciate the theorem's significance, it is essential to understand the problem it addresses. Directly computing torsion points on an elliptic curve can be a formidable task. The group of rational points on an elliptic curve, while finitely generated according to the Mordell-Weil theorem, can still be infinitely large. Identifying points of finite order within this infinite group requires a method to effectively bound the possible orders of these points. The sin B, fonso ord, dies pio, the so board, dies piece. More device stepping, D. The Lutz-Nagell theorem achieves precisely this. It provides a criterion for determining whether a given point on an elliptic curve is a torsion point, and if so, it provides a way to bound its order. Consider an elliptic curve defined over the rational numbers by the equation $($ equals sin x cubed plus x plus b $, where $, and $b are integers. The discriminant of this curve, denoted by delta, is given by the formula delta equals -16 times the quantity 4a cubed plus 27b². The Lutz-Nagell theorem states that if a point with coordinates x and y is a torsion point on this elliptic curve where x and y are rational numbers, then x and y must actually be integers. Moreover, if y is non-zero, then y² must divide the discriminant delta. The implications of this theorem are profound. First, it restricts the possible coordinates of torsion points to integers, significantly reducing the search space. Second, it provides a concrete divisibility condition involving the discriminant that the y-coordinate of a torsion point must satisfy. This condition further narrows down the possibilities and allows one to systematically check potential torsion points. To illustrate, suppose we have an elliptic curve defined by a simple equation, such as y² equals sin x cubed plus $1. The discriminant for this curve is -16 times 27, or -432. According to the Lutz-Nagell theorem, if xy is a torsion point, then x and y must be integers, and if y is non-zero, then y² divides -432. This allows us to systematically check the integer divisors of 432 to see if they can be the y-coordinate of a torsion point. We find that y can be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and so on. For each possible value of y, we can solve for x and check if x is an integer. In this case, we find the torsion points -1, 0, 0, 1, and 0, -1. The theorem allows us to methodically find all such points. Lutz's unique method for bounding the possible orders of torsion points involved a careful analysis of the properties of the elliptic curve and its points. She utilized the theory of algebraic numbers and the properties of the $p$edic valuation to derive her result. The proof involves showing that if a point is a torsion point, then its coordinates must satisfy certain algebraic conditions. These conditions, combined with the properties of the discriminant, lead to the divisibility criterion stated in the theorem. However, the original Lutz-Nagell theorem has limitations. It applies directly to elliptic curves defined over the rational numbers, or more generally over number fields. The theorem, in its original form, requires working over a local field, a field that is complete with respect to a discrete valuation. This restriction arises from the techniques used in the proof, which rely heavily on the properties of the $p$edic valuation. While the theorem can be adapted to other fields, the adaptation requires additional considerations and modifications, The theorem provides a practical method for finding the torsion points of elliptic curves. By reducing the problem to a finite search, the Lutz-Nagell theorem allows mathematicians to determine the torsion subgroup of an elliptic curve, which is a fundamental piece of information about its arithmetic structure. Though later generalizations and refinements have expanded its applicability, the original theorem stands as a cornerstone in the study of elliptic curves, providing a concrete and effective tool for understanding their torsion points. It is a testament to Lutz's ingenuity and her deep understanding of the arithmetic of elliptic curves. The Lutz-Nagell theorem, with its elegant formulation and practical utility, resonated deeply within the mathematical community. Its arrival provided a tangible method for tackling a previously intractable problem, pinpointing the torsion points of elliptic curves. This theorem, a beacon in the nascent field of arithmetic geometry, offered a concrete entry point for researchers seeking to explore the intricate arithmetic structure of these curves. The theorem's impact can be understood by considering the challenges confronting number theorists at the time. Elliptic curves, while geometrically simple, harbor a wealth of arithmetic complexity. Questions about their rational points, their group structure, and their behavior over finite fields were central to many investigations. The Lutz-Nagell theorem directly addressed one crucial aspect of this complexity: the determination of torsion points. Before its advent, identifying these points was largely a matter of educated guesswork and computationally intensive searches. The theorem transformed this process, providing a systematic and finite procedure for finding all possible torsion points. The theorem's statement itself, linking the coordinates of torsion points to integer values and a simple divisibility condition, gave mathematicians a powerful tool. It allowed them to replace an infinite search with a finite one, significantly reducing the computational burden. This was particularly valuable in an era lacking the powerful computing resources available today. The ability to explicitly determine the torsion subgroup of an elliptic curve opened doors to further investigations. Understanding the torsion subgroup is often a prerequisite for studying the Mordell-Weil group, which describes the group of rational points on the curve. The reception of the Lutz-Nagell theorem within the mathematical community was overwhelmingly positive. Contemporary reviews lauded its ingenuity and its potential for advancing the study of elliptic curves. The theorem was quickly incorporated into textbooks and graduate courses, becoming a standard topic in the curriculum. Its accessibility and its practical applicability ensured its widespread adoption among researchers. While the theorem itself is a statement about elliptic curves over the rational numbers, its proof relies on techniques that extend to number fields and local fields. The proof, which involves analyzing the elliptic curve over the $p$adic numbers, showcases the power of $p$adic methods in number theory. The $p$adic numbers, a completion of the rational numbers with respect to a different notion of distance, provide a powerful framework for studying the arithmetic properties of elliptic curves. Lutz's work demonstrated the effectiveness of these methods, paving the way for further applications in arithmetic geometry. The historical context surrounding Lutz's work is also crucial to understanding its significance. In the early 20th century, number theory was undergoing a period of rapid development. New ideas and techniques were emerging, and mathematicians were grappling with increasingly complex problems. The study of elliptic curves was still in its early stages, and many fundamental questions remained unanswered. The Lutz-Nagell theorem provided a much-needed tool for tackling these questions, contributing to the growing body of knowledge about elliptic curves. The theorem's influence extends beyond its direct applicability. It served as a catalyst for further research, inspiring mathematicians to seek generalizations and refinements. Several mathematicians built upon Lutz's work, extending the theorem to other fields and exploring its connections to other areas of number theory. These extensions often involved overcoming significant technical challenges, demonstrating the depth and complexity of the underlying mathematical concepts. While direct evidence of collaborations or interactions between Lutz and other researchers working on related problems is sparse in readily available historical records, the mathematical community of the time was relatively small and interconnected. It is highly probable that she engaged with other number theorists, either through conferences, publications, or personnants. The collaborative nature of mathematical research often leads to the cross-pollination of ideas, and it is likely that Lutz's work was influenced by, and in turn influenced, the work of her contemporaries. The absence of explicit documentation does diminish the likelihood of its existence. The Lutz-Nagell theorem's impact on the development of arithmetic geometry is undeniable. It provided a concrete and accessible result that helped to stimulate further research in the field. Its influence can be seen in the subsequent development of more general theories and techniques for studying elliptic curves. The theorem remains a cornerstone of the subject, a testament to Lutz's mathematical insight and her enduring contribution to number theory. The theorem, though initially limited in scope, offered a pathway to understanding the deeper arithmetic properties of elliptic curves. The significance of the Lutz-Nagell theorem within the broader landscape of number theory research at the time resides in its ability to bridge the gap between abstract theory and concrete computation. Number theory, by its very nature, often deals with abstract concepts and intricate relationships between numbers. The Lutz-Nagell theorem provided a tangible link between these abstract ideas and the practical problem of finding torsion points on elliptic curves. This link was particularly valuable in an era where computational resources were limited, and mathematicians relied heavily on ingenuity and clever techniques to solve problems. The theorem's elegance and simplicity also contributed to its widespread appeal. Its statement is easily understood, and its proof, while technically demanding, is relatively straightforward. This accessibility made it a valuable tool for both researchers and students, helping to popularize the study of elliptic curves and arithmetic geometry. The theorem's impact can be seen in the numerous research papers and textbooks that cite it, attesting to its enduring influence on the field. The theorem's restriction requiring working over a local field, a field that is complete with respect to a discrete valuation, proved to be a fruitful avenue for further investigation. This limitation, rather than being a drawback, highlighted the importance of $p$adic methods in the study of elliptic curves. Mathematicians explored ways to overcome this restriction, leading to the development of more general techniques that could be applied to a wider range of fields. These efforts, inspired by the Lutz-Nagell theorem, further enriched the theory of elliptic curves and expanded its connections to other areas of number theory. The accessibility of the Lutz-Nagell theorem, owing to its clear statement and relatively direct proof, belies its profound and lasting impact on number theory. This theorem, a cornerstone in the study of elliptic curves, continues to resonate within modern mathematical research. Its influence extends beyond its immediate applications, serving as a foundational result that underpins more advanced concepts and techniques. The enduring legacy of Elisabeth Lutz's work is multifaceted. The Lutz-Nagell theorem serves as a gateway into the intricate world of elliptic curves, offering a tangible and comprehensible starting point for students and researchers alike. Its statement concerning the torsion points of elliptic curves defined over the rational numbers provides a concrete objective for exploration. The theorem's proof, while technically involved, is accessible enough to be followed by those with a solid foundation in algebraic number theory. This combination of accessibility and depth has ensured its continued presence in mathematical curricula and research. The theorem's significance is further amplified by its role in the historical development of arithmetic geometry. Lutz's work, along with that of Lutz-Nagell, provided early impetus for the systematic study of elliptic curves as geometric objects with arithmetic properties. This perspective, which blends algebraic geometry and number theory, has become a dominant theme in modern mathematics. The Lutz-Nagell theorem exemplifies this interplay, demonstrating how geometric properties of elliptic curves can be used to deduce arithmetic information about their points. Modern number theory has embraced and expanded upon the foundations laid by Lutz. The Lutz-Nagell theorem, while initially limited to elliptic curves defined over the rational numbers, has inspired generalizations and extensions to other fields and algebraic structures. Mathematicians have sought to understand the behavior of torsion points on elliptic curves defined over finite fields, number fields, and even more abstract objects. These investigations have led to the discovery of new phenomena and the development of powerful new tools for studying elliptic curves. The connection between elliptic curves and cryptography provides another avenue for appreciating the enduring relevance of Lutz's work. Elliptic curve cryptography, a widely used method for securing online communications, relies on the algebraic properties of elliptic curves to create cryptographic keys. The security of these systems rests on the difficulty of solving the elliptic curve discrete logarithm problem, a problem closely related to the structure of torsion points on elliptic curves. While the Lutz-Nagell theorem does not directly provide a solution to this problem, it offers fundamental insights into the nature of torsion points, informing the design and analysis of cryptographic algorithms. The theorem's contribution extends also to the realm of computational number theory. Algorithms for computing the torsion subgroup of an elliptic curve often rely on the Lutz-Nagell theorem as a starting point. By providing a finite set of candidate points for the torsion subgroup, the theorem allows mathematicians to efficiently search for the actual torsion points. This computational aspect has become increasingly important as elliptic curves are used in a variety of applications, from cryptography to coding theory. Beyond the specific applications of the Lutz-Nagell theorem, Elisabeth Lutz's achievements stand as a testament to the power of mathematical inquiry. Her work embodies the spirit of exploration and discovery that drives mathematical progress. Her contributions to number theory have inspired generations of mathematicians to delve deeper into the mysteries of elliptic curves, revealing new connections and uncovering hidden structures. The challenges faced by female mathematicians in Lutz's era add another layer of significance to her accomplishments. Despite facing societal barriers and gender biases, Lutz persevered in her pursuit of mathematical knowledge. Her success serves as an inspiration to aspiring mathematicians, particularly women, who may encounter similar obstacles in their own careers. Lutz's story demonstrates that talent and dedication can overcome adversity, leaving an indelible mark on the world of mathematics. Elisabeth Lutz's work is more than a historical footnote. It is a vital component in the development of modern number theory, a testament to the enduring power of mathematical ideas. Her theorem continues to inspire research, inform cryptographic applications, and motivate future generations of mathematicians. Her contributions to arithmetic geometry have solidified her place as a pioneer in the field, whose legacy will continue to shape the direction of mathematical research for years to come. The theoretical underpinning that Lutz provided, even if not directly translated into cryptographic protocols, is crucial. The security of elliptic curve cryptography depends on the algebraic structure of the curves, and understanding the properties of torsion points, as illuminated by the Lutz-Nagell theorem, is essential for assessing the strength of cryptographic systems. Her work indirectly contributes to ensuring secure communication in the digital age. Lutz's influence extends beyond the purely theoretical.
The computational techniques developed to implement and extend the Lutz-Nagell theorem have found applications in areas such as computer algebra systems. These systems, used by mathematicians and scientists to perform complex calculations, often incorporate algorithms based on the Lutz-Nagell theorem for computing with elliptic curves. Her work, therefore, has a tangible impact on the tools used by researchers in a variety of fields. Elisabeth Lutz's dedication to mathematics, her groundbreaking contributions to number theory, and her perseverance in the face of adversity make her a remarkable figure in the history of science. Her work continues to resonate within the mathematical community, inspiring new discoveries and shaping the direction of research. The Lutz-Nagell theorem stands as a testament to her intellectual prowess and a reminder of the enduring power of mathematical ideas. It is a cornerstone of modern number theory, a foundation upon which countless other results have been built, and a source of inspiration for mathematicians around the world. Her legacy is not merely about a theorem, it is about the enduring impact of a dedicated scholar who pushed the boundaries of mathematical knowledge and whose work continues to resonate in the 21st century.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.